Hello everyone, this is Teacher Lou from Delta Learning Space. Today we are going to be chatting about significant figures and why they matter in chemistry. In this video I'll show you what significant figures actually mean, why chemists use them, and how we can apply them correctly. Ready? Let's go! Before I get started, I've linked a free significant figures reference sheet and practice problems below. You don't need them right now, but later on they can be a great help. All we need right now is just a paper and pencil. Let's start with what significant figures are not. They are not random math rules, and they are not meant to make chemistry harder. Significant figures, often called sig figs and abbreviated to SF, represent the precision of a measurement. They tell us which digits in a number are known with certainty, and which digits is an estimate or uncertain. So sig figs are just a measure of certainty. But now let's talk about what it means to be certain versus uncertain. When we measure something, we never know the value perfectly. Significant figures help us communicate that uncertainty. And that's because chemistry is based on measurements like mass, volume, temperature, length, and every measuring tool has its limits. Significant figures are how scientists stay honest about those limits. Let's take a look at our example below. For example, we have this paper clip that's being measured by this ruler. If we look at the zoomed in version of this, we know that our paper clip is at least 4.9. But we do have a space between that 0.9 and that 5, which means we have uncertainty in that hundredths place. I know that certainly this paper clip is 4.9 something, but then I have to make an estimated guess on what that number that's going to follow. And so here I have it as 4.92 with my hundredths place being this uncertain digit. And sig figs help us show the level of certainty that we have. For my example here, all of my digits are significant. My 2 certain digits plus my 1 uncertain one. Measurements are never exact and will have limitations and different levels of precision. Significant figures help us communicate those levels of certainty. And while chemistry uses math and numbers, it's based off measured data, and not all of the values that we have are going to be exact. And because of that, we need significant figures in our chemistry operations. Now let's practice the main patterns that chemists use to count significant figures with our 5 rules of sig figs. Our first rule is that all non-zero digits are always significant. Let's take a look at our first example, the number 34.5. All of the digits here are non-zero, and because of that, they will all be significant. And so this example here, 34.5, will have 3 significant figures. Take a quick pause of the video and try the next one. In example 2, our number is 41.9234. This number is comprised of all non-zero digits. And because they're all non-zero, they are all going to count as significant. So this one will have 1, 2, 3, 4, 5, 6 significant figures. While Rule 1 deals with non-zero numbers, the next few rules will deal with how we count zeros, and this mostly matters on their location in the number. When looking at these, I like to ask myself, is the 0 acting as a placeholder, or does it help us better understand precision? Rule 2 says that zeros between non-zero numbers are significant. Let's take a look at what that means in practice. Our first example, the number 2002. From the first rule, we know that these values count. So I'm already at 2 significant figures. Now I have my zeros in between. And based off my rule 2, these will also be significant. And that's because this number is not simply 2000, it's 2002. And so these zeros here do help us in understanding the precision a little bit better and are more than just placeholders, making them significant. Pause the video and try the next one. In our decimal number 0.1203, the same 2 rules apply. The non-zeros are going to be significant, And because the 1 0 that does appear is in between my non-zeros, it's also going to be significant. And this number will have 4 sig figs as well. Our next rule is that leading zeros, which are before the first non-zero digit, are not going to be significant. And when we're dealing with zeros, position really does matter because in Rule 2, the zeros in between were significant. In Rule 3, these zeros are going to be not significant. Let's take a look at our first example. Our first example is 0.0007. From Rule 1, I know my 7 is going to be significant. These zeros here are my leading zeros. They occur before the first non-zero digit even appears. And because of that, they are not going to be significant. They're only acting as placeholders, making this number here have only 1 sig fig. This rule is super helpful when we work with small decimal values. And I like to think that these zeros aren't significant because all they're doing is acting as placeholders for our non-zero digits. So when we have those leading zeros, they act as placeholders. They are not significant. Now take a moment, pause the video, and try the second example. In example 2, we have our 1 non-zero and we have our leading zero. Our leading zero is not significant, making this one have 1 SF as well. These zeros only help us locate the decimal. They don't add precision, making these zeros not significant. Our next rule is that trailing zeros, the zeros after the last non-zero digit, may or may not be significant. And I know we can look at that may or may not, and it sounds very vague, but we will walk through when those zeros are and when they're not significant. And while the previous rule was helpful with small decimal values, this rule is useful for both large and small numbers. But as we look at this rule, we have to keep in mind whether these zeros are acting as placeholders or whether they're helping us with precision. Let's take a look at our first example, the number 8,400. From the first rule, we know that my 8 and 4 are going to be significant. The zeros behind, these are our trailing zeros, and they're only acting as placeholders. And because of that reason, this will only have 2 significant figures. In example 2, the number 1.28900, these are also trailing zeros. But these trailing zeros will be significant because they're trailing in the decimal values. Thinking of precision, if our measurement only went to the third decimal place, then our number would have stopped there. Because it has 2 zeros after that, this is telling us that our tool can take that measurement to those decimal places. And because of that, these zeros are acting in helping us understand precision more than just placeholders, making this number have 1, 2, 3, 4, 5, 6 significant figures. Now pause the video and try the last one. This one's very similar to example 1, and the 8 and 4 are going to count. And these trailing zeros, because they extend into the decimal place value, they are acting as more than just placeholders. They are representing the precision. And because of that, all of these zeros are going to be significant, making this number here have 1, 2, 3, 4, 5 significant figures. And a general rule of thumb that I like to follow is if my trailing zero doesn't have a decimal place, it is not significant. If my trailing zero does have a decimal, it is going to be significant. Finally, we have our last rule, and that is that exact numbers have unlimited significant figures. And that's because these aren't based off measurements, and so they shouldn't be limited. Our first example is the exact conversion between a foot and inch. And this conversion is that exactly 1 foot is equal to exactly 12 inches. And because of that, we have unlimited significant figures. The same applies to a very applicable chemistry number here, 6.02 times 10 to the 23rd molecules. It's a value that you are going to get very familiar with called Avogadro's number. We also treat this value as exact as well. We actually have this defined as 6.02 214,076 times 10 to the 23rd. Even though we often see Avogadro's number rounded in textbooks like we have above, it is actually defined as an exact value, and so it's often treated as having unlimited significant figures as well. But I would definitely check with your teacher and how they're treating this number. I know that sometimes these rules can be overwhelming, but the more we practice, the easier counting them becomes. But as a quick recap, non-zero digits always count, and zeros depend on the position. We've seen the rules. Now let's see some of these rules in action with some operation practice. First, we'll explore addition and subtraction. When we add and subtract, our answer should be rounded to the same number of decimal places as the measurement with the fewest number of decimal places. Let's check out what that means in action. Our first example is 0.07 plus 2.305. I'm just going to stack these so we can better see that. And if I do this math, I will get 2.375. But based off my significant rules above, I have to round to the same number of decimal places as the measurement with the fewest. And so my fewest is occurring in my 0.07 because I only go to the hundredths place. And so that means I need to round to the hundredths place as well. With the appropriate number of significant figures, this means that this is going to round to 2.38. Remember, our rules aren't about math, but about honesty in the values that we can calculate. Now let's take a look at another example. Take a moment to pause the video and try the subtraction problem. Doing the subtraction gives us 111.7965. However, my fewest number of decimal places is occurring here, and I can only round to the tenths place, making this value with the correct number of sig figs equal 111.8. And remember, when we round, if I'm rounding here, I'm looking at this number behind, and that's going to raise that number if it's 5 and above. We're in the home stretch now. When multiplying and dividing, our answer should have the same number of significant figures as the measurement with the fewest sig figs. And this is where those counting rules are going to come in handy. Always count your sig figs before you do the math. Now let's check that out in action. Our first example is 204.3 times 6.5. Before we do the math, let's count how many sig figs each of these values have. 204.3 will have 4 significant figures, and that's because I have 3 digits that are non-zero, making them significant, and the 0 in between is also going to be significant. My second value only has non-zero digits, making them both significant at 2SF. And so that means when we do this math, I'm going to round to 2 significant figures. Multiplying this value here, I just did this in a calculator, we'll get 1,327.95. But because these are chemistry numbers, our multiplication rule says we have to round this to the fewest number of sig figs, meaning we have to round it to 2 sig figs. When I do this, I start from the left, and my 1 is significant, and then my 3 is significant. So those are my 2 that are going to count. I take a look at the number behind, but it's a 2, so it's going to stay, making this number 1,300. And I think this rule helps us understand a little bit more of why those trailing zeros without that decimal place, why they don't count. And that's because this number wasn't exactly 1,300. It was 1,327.95. However, because of our limitations with our decimal places, I have to round that to 1,300. And that's why those zeros in our rules before don't count as significant. Now it's your turn to try. Pause the video and try the division problem given. When doing these problems, I always count my sig figs. This one here will have 1, 2, 3, 4, 5, 6. Because that 0 is in between, it counts. And then my second one will have 3 sig figs. So that's my limiting factor, meaning whatever answer I get, I am going to round it to 3 significant figures. Doing this division problem, and I just did this in a calculator, will get us 244.4076, and that's going to trail for a bit, but that does not even matter because I'm going to round to 3SF. I start from my left and count 3, 1, 2, 3. So those are going to be my 3 significant figures. I don't even need to include anything in the decimal place because if I add zeros here, that's going to make those zeros significant. And so to round to 3, I'm going to leave this simply as 244. When doing calculations, always be careful of rounding too early. I know in our examples we only took a look at one-step problems, but this will be especially helpful when you do have multi-step. When you add or subtract, it's important to focus on the place values. And when you multiply or divide, it's important to focus on rounding to the value with the fewest number of sig figs. Amazing, we made it to the end, and so here I've left you with a few mixed practice problems. Take a moment to pause the video and really try these on your own. Thank you so much for joining me. I hope you found this video helpful as you work to master your chemistry skills. All of the rules we covered today can be found on that reference sheet, and if you want to try more problems, check out our practice problems PDF. Finally, if you want a quick recap, you can always check out our related blog post. All the resources can be found in this video description, and we can't wait to see you next time. Thank you so much and have a great day.